this is a really informal presentation, and informal really means I might be wrong. I'm talking about things that at a conceptual level, and I'm not, of course, really someone who practices deep networks or transformer networks. So I've learned some of this from people like Raul taught me some of those things and others. But I think it's useful as discussion. It's something that we're all confronted. So here, roughly, what I'm trying to be doing or trying to do is briefly lay out the basic concepts that connectionism and then deep networks and transformers use at a very macroscopic high level. And then examine the claim that floats around that these are potential models of the human mind, and clarify then what that would actually mean if they were. And then briefly sketch how, in which sense DFT could be a neural theory of the human mind, and sort of end only in the end really come back to a more technical comparison. So I don't have to go through all the slides. We can also just interrupt and discuss and so on. I think it's more interesting maybe to interact about those things. I have maybe like 40 slides or so, but there's very little on those slides. It's not a lot of facts, more really thinking. Good. So, connectionism, of course, was maybe the first proposal for a neural theory of understanding the mind. And it's in that spirit that all of this will now be reviewed. And I would say connectionism has maybe 5 or 6 key ideas. So the first key idea is, of course, that neurons are these simple summing and thresholding elements. And that's an idea that we share, I would say, in DFT. We're part of connectionism in that sense. And it has the critical idea that it is the connectivity that determines the function meaning of activity in any particular sense. This is like one of the very old networks, right? And when they write down here seed for a neuron, then the idea is that that is just a label that the modeler puts to that unit, but the fact that this unit stands for the word seed is really only established by the fact that it will be activated when a certain pattern arises in its input level, and it's the connections to that input level that gives rise to that function. And so I think that is actually a point of confusion, but we certainly commit to that as well in DFT. And maybe a very colloquial way of putting it, it's maybe say, well, hidden layers are critical for achieving cognitive function from neural networks. That was maybe a major obstacle initially to that realization. It essentially gives that associative power to the neural networks. And I would say actually it is related to the idea of binding in DFT. So what the hidden layer means is that there are a lot of neurons that are shared across other neurons. I took exactly, this is the old McLennan type model, which is actually almost symbolic because there are categories here. And the idea is that these neurons share connections to the hidden layer, or the hidden layer as neurons are shared substrate for these different concepts. And that's something that we use in binding. We have some shared dimensions. So I'll come back to that. Then, of course, there is this idea of learning. And I want to clarify right away that, of course, in our perspective, the learning of connectivity in connectionism and all the other deep networks and so on is really more something like fitting, right? That is determining the connectivity based on knowledge about desired output. That will be the most extreme, supervised. But unsupervised isn't really so different because it's also really knowing what inputs are and telling the network exactly when there are inputs like that present. So in that sense, it's also quite supervised. And then, of course, reinforcement learning is also just mildly more autonomous because you tell the system what the value of the output is. So I would say this is a source of much confusion in the discussion, especially the popular discussion about that. The word learning is used in a very different sense from the word, the meaning of that word in psychology, in learning from experience, right? The process of learning from experience is not really anywhere near approximated by these kinds of ideas in connections. And then maybe the fifth idea is having these architectures.
Gregor,
Yes, please.
A slide before, I don't know, where would you put the contrast networks in there? Where there you have like two networks that supervise each other. Thinking of Jochen Trisch's work.
I would say there is, of course, a gradient, a continuum into forms of learning that might be ultimately more autonomous. So, for instance, I would say that some reinforcement learning type networks might approach a little bit of autonomous learning. Autonomous learning would be when you have a network that actually can generate behavior in some way and therefore can create experience and creates its own data. And it would mean that the network has some way of, detecting that this is now a learning instance, that now I'm updating my weights because currently I'm going through a learning experience. And I would say there are some networks that sort of approximate that a little bit, but very typically I would say that they're very limited in doing that. And part of that is that they don't really have behavioral autonomy. They don't really generate behavior on their own. I don't remember that specific network, so I'd have to think about it.
Yeah. There have been a few kind of applications of these, they're called general adversarial networks.
Yes.
To speech, where you have one part of it just basically randomly generating outputs.
Yeah.
And then you have another network, basically they're independent, that's doing like the categorization. And they've just through this process of like randomly generating and then categorizing, they come to achieve like, so they kind of like learn something about the speech that then generalizes to kind of new instances. So maybe that's this kind of like in between case.
Yeah, it reminds me of the talking heads, the what's his name, at Sony Lab, where there is some dynamic, means ultimately multiple agents that talk to each other, and one could think of that as some sort of metaphorical instantiation of autonomous learning in that way.
Luke Steels, if you're looking for the name.
Luke Steels, exactly. Yes, thank you. That was Julia, I guess, right? I have not seen everyone.
Yes.
Yeah. So there is, I mean, I'm sort of simplifying and drawing large contrasts because I would say it's very undeveloped. So if you think everything we know about development, for instance, the learning of language, of course, which is a major topic in psychology, then we would say we're quite far from having models that reasonably do that. And that's kind of interesting in the history of connectionism because originally a lot of connections actually connected to developmental data. And they were looking at things like how, for instance, the vocabulary grows over time and how that happens in a neural network. But I would say it was done in a model fitting mathematical psychology sense, that certain curves emerge from the model, but not that the model would actually be consistent with the process of learning, of what infants actually do when they do that. And it was actually doing, for instance, doing back propagation and which is as a process of course totally non-realistic. And then that process, that mathematical model leads to a similar curve. And I would say that's more in the tradition of mathematical psychology of saying, oh, the model is like, it describes something, but it isn't really anywhere near a process model. It's already something we will get into more. Good. So there's more to unpack here, and I'll come back to learning later. So the other thing is, of course, that the neural networks themselves are always architectures, and in a similar spirit, I would say conceptually they are dominated by feed-forward thinking, even though technically that's true, not true. There are recurrent networks, but they are conceptually, I think, often feed-forward in the sense that they are used in an input-output manner. And that's how a lot of connections thinking is actually still also somewhat information processing thinking. With the recurrent networks primarily used for sequences, and the current the deep neural networks are actually some trick of how to do that without recurrency. It's not entirely true, of course, because, for instance, DFT is part of connectionism, I would say, and attractor networks are using recurrent connectivity in a conceptually important way. So that overlaps, and there are some networks that are like that, and Boltzmann networks and Hopfield networks and so on. But I would say that the way the logic and thinking about connected networks is still quite strongly dominated by input-output thinking. I think that's also true about a lot of the deep networks. Good. So the deep networks added a few concepts, which, I'm just put it, not historically, it's a bit more complex. So certainly this idea of convolution, which took visual space primarily, and then other spaces as the grounding. So that's very consistent with sort of broadly the functional architecture of cortex, and Fukushima, you could say, is already sort of anticipating that idea. And that's also something shared with DFT. And there is the idea there that the connectivity would be to some extent homogeneous, that is across the space that is being sampled by the input. You would have the same weights at different locations. It's then done sometimes explicitly, actually routinely done in the early days by explicit weight sharing, which is a shortcut, it's not biologically realistic. We don't do that, so we actually think about that in DFT. But roughly this convolutional nature and the homogeneity assumption about connectivity is also consistent with DFT. The other special trick, of course, is this avoiding the recurrency, that is dealing with time as a propagation through the layers, which is sort of a computational trick that simply makes it possible to learn and simplify and so on. And that's a specific commitment that we don't share, and that makes that the layers are many more than the layers in the brain. So it's not a one-to-one mapping in that sense. Also, I would say a special idea is to use recurrency in these special ways. So the LSTM, which is quite important for the deep networks to be able to do, these networks are largely input driven, but they can keep states around by having these LSTMs. And I would say conceptually, it's sort of like working memory, but at the individual bit level, for every neuron. It's not at the pattern level. And I would say DFT is much more saying that the working memory is actually in units of, ultimately, of objects or action intentions. So really macroscopic and not at this microscopic level. So we'll come back to that, how distributed versus localist. And in some cases also used for gating as a part of the mechanism in LSTM. And then one can sometimes just isolate that mechanism and switch on and off certain branches of a network. But that's a special trick that we're not literally using in this form, even though some of our networks have some form of gating as well. And then there is maybe the softmax, which to my knowledge goes back maybe to Poggio and Riesenhuber, which is essentially a normalization mechanism on readout, so avoiding some of the problems that we're all aware of. And that's, of course, routine method, very important for the learning, for the backpropagation to go through these layers. And well, we also use gain control kind of mechanisms. For instance, I'll briefly review that in this last presentation. So that's sort of the idea. So the one new idea in transformers is, of course, the attention network. And I did try to understand that a little bit. Of course, there's a lot of technicalities there, much more than I understand or that I can use. So that's a little odd one, and I've tried to make it to make a caricature of that so that we can talk about it better, the simplification. So in many cases, one can think of the data as being a sequence of tokens. So tokens can be words, for instance, or letters, or some discretized set of instances, tokens. And so the T would be here time, but discrete. So they get these different entries, and X could be a very large vector. And the idea is to split these into three subvectors, a query vector, a key vector, and a values vector. And that's learned. The deep network would ultimately learn that. So that the query at a particular time t is combined with the keys at other times, neighboring times, And that this multiplication here is essentially the neural network associative multiplication. So that would fish out the matching, the key, the moments in time, the key that matches. And so the softmax on that would be then some weight of how well that particular key matches, and then transmits the value that corresponds to the matching key. I think I should be T prime here. Should be T prime. Sorry, I made a mistake. This should be T prime. So so what you're actually transmitting, this matrix multiplication, when this one is actually a sort of 0 to 1, a normalized weight, it's in that sense, it's a rate code thing. What this does is just transmits yes or no certain components of the V. So it's a way to transmit information like in a switch, and the switch is based on a query to key match. Of course, it's not discrete like that. It's using neural network associative power. Again, it should be T prime. So that's very particular. If it wasn't all learned, it would be almost like SQL, right? It would be like, I'm repeating the same sentence here, like with relational database thinking. This is very abstract analogy, but in relational databases, you're also using, using an index you have many entries that will be data. Actually, I have a slide here from a textbook. You have tables of data. These are values that have properties. They are keys. And then you can use indices to fish out all the entries that, match a certain value of the key. Like, all the teachers that teach a particular course. And by having in a department, different departments, you can find out here. This is an example of all the instructors and teaching a certain course that you could fish out, and then you can look up properties of those. So it's a little bit unusual in neural networks, because what you really do is you transmit some information, right? It's not usually we think of association as hetero or order association. I didn't hear that, I'm afraid. Can you repeat that?
I don't think that was a question.
Okay, maybe it's
somebody
just,
unmuting.
yeah. So it's sort of transmitting. In that sense, it's a little bit more like information processing, that you can transmit something and you have a switch, and the switch uses sort of association. While in classical connectionism, it would be the association itself, hetero or auto, that is the output, and it's the result of that. So, and that's why it's maybe so powerful. In fact, kind of interesting that it's sort of related to information processing. And so one thing is that is not actually an obvious neural mechanism. There's some special mathematical trick. Good. That's a little bit the things I would say are sort of the key elements. Of course, there are many other things as well, technical things, and the field is famous for not being always so theoretically clean. They would use all kinds of things. So in which way are they being used? What are the functions for those? And I would say for deep networks, conceptually, the primary function is, of course, ultimately categorization, classification. And I took this from Rolf's talk last month. And I would say that's sort of the core idea. And there's the idea that these would be invariant, that across all during the learning, you extract the features that are really characteristic of these categories and invariant under all the different shapes and forms they can take. So that's very powerful. But there are also other things, of course, extracting the feature dimensions, extracting the invariant dimensions, the latent dimensions, ultimately extracting, decomposing, independent, PCA and so on, extracting independent components, and ultimately capturing some kind of covariance or compression. And then, of course, generative networks, which now with deep networks have become very powerful. So where you don't put out something low dimensional, but something high dimensional. By having a compression, you can base that on sort of the regularities that are encoded in bottleneck of the network, and there are other functions as well. So still, these would be functions I would claim that are all in spirit rather input-output oriented. While I would say the key conceptual step made by transformers is this prediction idea that you have sequences that be still input-output, because you have your starter sequence and then you generate something from there. But this sequential idea is maybe going a little bit beyond what was previously done, and that's currently in the language domain. And for instance, similar for action sequences is really a step forward that is, creating all these impressions that it's so human-like. Okay, so when these networks, and I'll take the most recent ones, are used, are presented as a model of the mind, what's at space. And I think there's a lot of nonsense out there in the sense of people being somehow intuitively impressed. I find it so amazing that when you listen to some of the researchers, then you can see that as they talk about their feeling when they get the answers from GPT or something, then they think some magic happens. It's almost like they're losing their scientific sober mind, I think. Well, I mean, the most obvious point is it's a Chinese room, right? It's I think exactly a Chinese room. I remind you, the Chinese room argument that you could have a human in a room that doesn't know any Chinese but has a perfect rule book. That would be the learned thing, perhaps, and just get some arbitrary symbols thrown in on one side, and then knows how to answer based on that rule book, throwing the symbols out there on the other side, and then that human inside, or the group of humans, wouldn't actually speak Chinese and know what one is talking about. There's been a lot of debate about all the assumptions that go into that, and I would say these models are, in the first approximation, pure Chinese rooms, and the debate is then only if maybe human cognition is just like that. We don't know anything else either, which is a wild step and certainly not consistent with what you think. Or we think, well, that's exactly that. It's just an emulation. It looks like that. And so it lacks perceptual and action grounding, right? So you would certainly say that you don't know what you're talking about because you couldn't do any of the grounding problems. You don't know what it's talking about. But of course, there are people who work on that, and it's a question if you could fix it by having a network. This is an example, recent work of having a robot that has an actuator and a vision system. Is actually digital simulation that would have a transformer network inside, where there could be language encoding, could have learned certain sequences from language, and also has encodings of the visual scene and then ultimately of the action spaces, and then could get some details of that, but could start to orient actions in the world based on some input. And then, then it's maybe, in some sense, it's still a question if it knows what it's talking about or what it is doing, but it would have some form of grounding, right? And so it's a question if that would then overcome that difficulty. I'll come back to that, but that would be a challenge, perhaps. So one could perhaps still say, well, it's only emulating behavior, like the way humans would do that. It isn't really doing it like the real human does, and that would be visible from the fact that it could emulate a human acting, but it could also emulate some arbitrary game that violates the laws of physics, the laws of human behavior, or whatever. It could do anything, like a computer game that does something magic. It could just as well learn that, right? And that's what I now wanted to explore a little, and really ask, what does it actually mean to have a neural theory of the human mind? And I think that this is where I think our DFT philosophy, at least mine, is a little bit different from what most people think. And I had occasion to try that out in discussions. So I think that a neural theory of the human mind means a theory that explains the laws of the mind by connecting them, by establishing the logical connections between laws. So to see why I'm talking like that, think of physics, you could say the laws of physics are connected. And so when they're connected, then we talk about something being explained, right? In physics, we don't really explain anything. We just, as such, when we say, the law of free fall, that's just a description of some regularity, a constraint in nature. And when we use explanation, then we mean that different laws are in some way connected, so often not actually unique, the direction of who explains what. It can be done in multiple ways. So the classic example would be Galileo's law and Kepler's law, are linked by the Newton equation. In that sense, the Newton theory of gravity explains these two laws by linking them, by saying that thing that causes free fall is actually what causes planetary motion. And there are many other examples that can think like that. So it's not as crazy as it maybe initially sounds. And so, in the human mind, you have laws that would be, for instance, laws of cognition. I'm listing a few that are within reach of what we're doing. And you have laws of the brain, of neurophysiology, some of which are captured already by the frameworks, like the properties of neurons as summing and thresholding, and then we would say maybe stability properties and the fact that most connectivity is recurrent in the brain, and feature spaces and gain fields and so on. These could be laws, lawful or regularities of the mind, where the brain is an arbitrary, has particular structures like that. And then a possible theory would be something, for instance, let's say in our approach, explaining intentional bottlenecks from the binding and coordinate transform problem that I'm alluding to work that we did, where we are seeing that, because we can't have very high-dimensional representations, and so we need binding through space, and binding through space requires one item at a time, and that actually makes it possible to link things in different coordinate transforms, just having with a single coordinate transform machine. That would be sort of an argument, an example of an explanation. We would explain the attentional bottleneck, and that really means that we're linking different constraints like that together. So that's just sort of the abstract way of thinking about that. So in cognition and in neuroscience, people don't often talk about laws, and maybe theoreticians might be happier if we call it constraints. And that is a little complicated, and the history of thought in this field is a bit different, where people talk about predictions and model accounting for data and fitting data and so on. So there's this whole area of that. And so I think from the logical point of view, a lot of these laws could be just assumptions of a model. And because you assume that it's a structure, like I'm listing the concepts, and these concepts could also be thought of as making assumptions about the brain or the cognition. And that has the same status as law, as long, if these assumptions are then consistent with some empirical facts, then they are justified. And whether they are justified as assumptions or they are predictions is actually not logically different. Sometimes there's some confusion about that, I think, in the literature. And when you say models account for data, this is also complicated in that there are some ways how data, for instance, can be then predictions the model makes, that they could be really deep, in the sense that with these assumptions, only that kind of predictions from this qualitative prediction would be possible. While there could be other cases where you're able to fit the data, but you could also fit data that are different from the ones that are real, and then that's a much weaker constraint. So this is a whole kind of worms there. But still the overall idea would be that a neural theory of the mind would have to do that kind of work, linking all kinds of different phenomena that are captured as constraints through a theory that connects them all, right? And neural and cognitive would mean that some of these constraints come from the neural domain, and some of these constraints come from the behavioral domain. So I wanted to be a little bit more specific than that to get to DFT. So what are these kinds of constraints? And of course, it would be now a whole we could, the whole summer school or our teaching and work is about all of that. But one could say maybe very macroscopic level, what we're looking at is constraints that come ultimately from evolution and from development, I would say. So certainly we're under this hypothesis that cognition emerges ultimately from sensory motor behavior in evolution. That is, organisms start out as motor sensory machines, and then as we look at further in evolution, the human brain and the mind are building on that and becoming more less sensory motor, more abstract, are more able to go beyond sensory motor. And so, for instance, in DFT, that means that certain properties from that from that history are reflected in how the brain works. I'll come back to that. And then analogously, we know that in development, there is a much more sophisticated or subtle point. There is a transition from sensory motor to cognition, that cognition is building in development on sensory motor, and sensory motor is very important for actually acquiring some cognition. So in that sense, autonomous learning is also really a central constraint for the human mind, that you're open to that you can understand that it is the product of development that you're looking at. And so in DFT, this shows up as the DFT framing of embodiment and grounding, perceptual grounding. So we're not actually those people say that you always have to move when you think or something. We're fully aware that you could have purely models of pure mental activity, but the models are still constrained by embodiment and grounding in that certain properties are inherited. So these properties of stability and continuous state, and then the embedding in low dimension spaces, which ultimately enable the link to sensory motor, so that there is no discontinuity. It's not that suddenly you have an interface, and from then on it's higher cognition, and before it was all so sensory motor. And so I think that's the source of difference. So when we're not talking, thinking back about transformer networks, for instance, that we could say, well, this is a real constraint. It has to be possibly emergent from sensory motor. So we've framed DFT as a neural theory like that. So by embracing constraints that come from that history, and then assuming making more concrete assumptions. I'm not listing them all here. So assumptions like that neural populations are the relevant level of description, and that there's strong recurrency. So interactions within populations are very important. That leads to the notion of localist representations. That leads to the notion of low-dimensional representation. Once you have localist, you have that, and that leads to the need for binding. So hinting that there are a lot of constraints within DFT that come from committing to some of those laws, some of those principles. So and that's where it's important then to examine which of these assumptions we share with these other approaches. And so one central element of that is this notion of autonomy. We've always struggled to exactly say what it means. It's this idea that the neural processes emerge from neurodynamics, from these neural networks, so emerge autonomously on their own. So no external device that reads out like a clock, a computational cycle, and so on, to reads out the different sequences. So sequences, just by stepping through some input or having some computer program that steps through something, isn't allowed, and that is reflected in the alternative to that is often this function calling notion that mental activity is applying a function, calling a function, firing the rule in classical cognitive architectures, and then when the function is done, it returns control, and you're calling the next function, and so we would not call that autonomous. And so that is certainly a kind of constraint that is quite unique to DFT. I would say that many other neural networks don't really make that commitment to this kind of autonomy. It's a major constraint and it's very difficult actually to get it right. So stepping back a little bit, this means that if we think of DFT as a potential neural theory of the mind, what we're specifically hypothesizing that the mind is a specific thing, a specific architecture that reflects these constraints. it's so reflect in the brain, the mind and the brain, both have the specific structure, and so actually not a general intelligence. So I mean, that's, in other words, whether there is some abstract generalization from that one could call general intelligence is then another question, but it's really quite specific about the sensory motor surfaces, with all the order in which this emerges, and all these properties that are just listed. So it's also an idea that's specific. So if I wanted to be polemical, I would then radically say the deep neural network transformers are neither neural nor theories of the mind. And so not neural in the sense that they have some key elements that are not neurally plausible or not elaborated how they could be neurally plausible, with the layer structure, the recurrence not really captured well, the attentional mechanism isn't really mechanistically obvious, and there, the learning rules and many other things that are not neurally plausible. And they're also really missing key functions. So I would say it's really these two. It's the autonomy and related autonomous learning, the true developmental element that we discussed before. And they're also not really aimed at capturing laws of the mind. I would say, I mean, there's certainly not a concern for most people, and maybe they can sometimes do that. But it's that subtle issue, because you could, of course, emulate the mind by having that in the data set from which you learn. You could have some regularities that come from the human mind, and then it looks like the model has properties of the human mind, but really just because you fitted it to these parameters, because that's in the data. I think that's happening a lot with large language models right now. But there's nothing in the structure of these models where that's necessary. They could just as well do it differently. For instance, they do parallel processing. They don't have an attentional bottleneck, but they could emulate an attentional bottleneck by just building that in. So that fact that they don't capture the laws of mind leads to them often having this superhuman performance. And that came up in a discussion we had at the INI, and I realized there was a lot of discussion. People were talking about, are these things, these systems, better than humans, or what is it then that only humans can do? And thinking, well, that must then mean that we have a theory of the human cognition if we find the things that only humans can do. And I think that is actually quite misleading. So this performance view of neural networks, I think, is a subtle slip into abstract computational theories of the mind, not neural theories of the mind, where you essentially describing the function by some approach without actually really being interested in the laws and the constraints. So disconnected from the sources of constraints, from evolution and development and so on. So I think that's a very misleading angle. If there is superhuman performance, always a hint that it's not actually human, just like a spreadsheet isn't human. This SQL isn't human. So I end on making it more concrete, and this would be actually really a research program that I obviously haven't done, when one thinks more concretely about these differences now. So I would say we're certainly sharing a lot of assumptions, certainly with connectionism, and then also with even the more advanced networks. So of course, the activation, summing, thresholding, the connectivity as the source of function, the fact that maybe something like hidden layers or shared dimensions are critical. We need to elaborate that a little bit more. Maybe the important role of the 2D sensory surfaces, actually not trivial that they are 2D or low dimensional. The ideas of homogeneous networks and convolution, the fact that low dimensional feature spaces may be emergent or maybe natural in some way. Maybe we're also agreeing that higher dimensional features are important for categories, and that categories do invariance. We're using nodes and concept nodes and so on for that. So that's consistent. Maybe also the notion of gain control, or the problem of gain control, that you need to be able to transmit information in a more flexible way and not just have rigid thresholds and so on. While I would say at the technical level, there are some obvious points of divergence, but these are more or less technical. So for instance, certainly we don't do the weight sharing. which is a real constraint. If we don't do weight sharing, then we have this problem of coordinate transform. So if we don't find it plausible to learn, continuously many copies of a relational operator, let's say Matisse's work, for instance, or Julia actually initiated that on larger to the left of and right of and so on. Then when you don't do weight sharing, then to apply that to new locations, you need to do coordinate transforms. That's a major constraint for our models. And then, of course, this commitment to autonomy means that we're not unfolding the layers. We're really doing the recurrence in the strongest connectivity is recurrent. And we're thinking of working memory and state as being at the macroscopic level of these representations, the object level, and not at sort of the bit level. So we're not, therefore, able to encode distributed representations only for special cases like discrimination. And most of the higher levels of cognition that are independent of running input are, in our theory, localists. And that's a major constraint, major point of departure. And I'm very interested, and if Julia is still here, to hear about her new views on VSA. I think the vector symbolic architectures, there could be a real point of, one could think more deeply about that point of divergence and question it or ask about it. And finally, we don't have this SQL type of attention, but we do have, queue matching and attention bottlenecks, and I don't think they have the same function, but could say maybe something like a queued activation, queued recall of not just of memories, but of context could maybe be somewhat similar. Most fundamentally, I would say that the fact that we're committed to these localist things, the attention, the attractor instability-based autonomous processing, where we then achieve high cognition through these sequences of instabilities, mental maps, and so on. And so that is ultimately the embodiment constraint that, in fact, for instance, we're even now thinking that maybe we need these grounded representations for anything that has some kind of contents that you don't have symbols to shift around, right? So you can't actually do logic with some abstract rules. When you do inference, you have to ground it. And maybe that explains some of the typical logical mistakes people make, that they always do it in a grounded form, and they effortfully lift that, the ability to think more abstractly is sort of gained by using analogy, and we have some accounts for how that could work, lifting from the grounding level to more abstract levels, but always having the signature through the grounding. So that would be a possible point of divergence as well. So my closing slide is, I would say, if we then think where DFT stands, then we still have lots of space to go toward higher cognition, because we only started to do very little there, and some of the transformer network can emulate what looks like higher cognition astoundingly, and that's a difficult thing. And actually, Boris wrote an email, I don't know if he's here today, about that, and I thought that was very interesting, and Julia also raised the point about that can we actually compete with these kind of models, and I think that's probably very difficult, because an account that is consistent with all these constraints is very constrained, right? And if you're not constrained by that, then you can go for simpler solutions that might outperform what we do. And the other is autonomous learning and development. Julia worked actually for some years on that, and I have a true appreciation of the difficulty in there, and we encounter that in developmental work. And John is currently, I think, facing problems like that as he's looking into process models of word learning. Okay, maybe that's as much as I'm pushing that.